So you might say, okay, why is the coefficient a minus 1 so important? So before we, so this is the subject of Cauchy's residue theorem, okay? So before we prove Cauchy's residue theorem, let me just prove a lemma. And the lemma is that, consider the integral in.
Sir, what is a lemma?
A lemma is like a short result that helps you prove a bigger, more important theorem. Lemma is like it's kind of a mini theorem that you use to prove
Like a staircase to a bigger stair.
Exactly, yeah. So let's define I of n to be the contour integral around a small circle of z to the power n, where n is an integer. So this is a class of contour integral. So S1 is a small circle of, say, radius epsilon, and around some point, right? Around, say, the origin. If it's on the origin, we can always do a coordinate transformation to bring it to the origin. Okay. So now we see how to do a contour integral in action. So we have to somehow parameterize the circle, right? So one way of parameterizing a circle is by an angle theta, which goes from 0 to 2 pi. So if I do this, then I can define z. I can say z is equal to some real radius times e to the power I theta, right? Do you guys agree?
Yes, sir.
Okay. So then I of n is going to be, oh, by the way, before I do that, let me just also do this. Then if I take the derivative of z, then epsilon is constant because it's the radius of the circle, right? So what we'll have is I d theta e to the power I theta, right? And this I can write as I z dz. Okay, because epsilon and this guy makes me this. Sorry, I am not dz, d theta. So this is I z d theta, right? So now I can evaluate I of n, which is just going to be, so what was this? This is S1 f of, z to the power n d of z, but this is nothing but an integral from 0 to 2 pi, and dz has an I in it. The integrand was z to the power n, but now we have a contribution z from the measure, so it becomes z to the power n plus 1, and then we have e to the power no, sorry, we don't have e to the power yet. We have d of theta, right? Okay, so do you agree?
Yes, sir.
Okay, so then we can say, okay, what is z? Z is, it's given here, so let's write that. So we get 0 to 2 pi. We get epsilon to the power n plus 1. And we have e to the power I n plus 1 theta d of theta, right? Okay, so this is what my integral becomes. Now notice that if I have an integral from 0 to 2 pi, and the integral is of dik theta d of theta, and k is an integer, but not equals to 0, then what is this integral? Can someone tell me?
1.
Okay, someone else?
Zero? Because I feel like you're integrating around a circle.
Right, I mean, what is the real part of this? It's a cosine, k of theta, right? And the imaginary part is sine k of theta. And you know that as long as you integrate sine and cosine over some 2 pi k, where k is an integer, it's going to give you 0. Right? So, if you don't believe me, let's just do this, okay? So this is e to the power I k theta divided by I of k, right? And we have 2 pi and 0. Of course, and this is 1 over ik. What is e to the power I? E to the power ik 2 pi is 1, right? Because k is an integer. Minus 1, e to the power I, 0 is 0, right? So this is 0. Okay? So this thing is 0, as long as k is a non-zero integer. So if I use this in my above integral, then we see that I of n is 0 if n is an integer. When is it non-zero? It's only non-zero when this is 0. When this is 0, this guy is 1. When this is 0, n is 0, this guy is 1. And in that case, we are just integrating d theta from 0 to 2 pi. So in that case, the result is 2 pi I. Sorry, let me let the cat out. Okay, so it's 2 pi I for n equals 2 minus 1 and 0 otherwise, right? So let me just recap. 1 over 2 pi I z to the power n of d of z over s1 is 1 if n is minus 1, 0 otherwise. Okay? Do you guys agree?
Sir, is S1 a closed loop or a circle?
It's a circle, but it actually can be a closed loop too.
Okay.
Why is it a closed loop? So suppose that you're doing the integral over a circle here, right? And you want to deform this integral over a closed loop like this. Now, as long as in this annular region, this is a topologically like it's not simply in this annular region. Suppose that your function doesn't have any singularities. Okay, then if this is, say, this is S1 and this is C, so in the yellow region there are no singularities. Then if your f of z of d of z is 0, then you can show that this is also over S1, that this is also true for the bigger thing, or the deformed contour. Okay. And how do you show that? Because by Cauchy's integral theorem, the Cauchy's integral theorem says that we have a curve. If we have a curve like this and there is no singularity here, then the integral over this curve is 0, right? So this curve consists of two contours, say gamma 1 and gamma 2. So my contour integral is the fact that it's f of z is 0, but I can write that as is the sum of contour a contour integral over gamma 1 plus a contour integral over gamma 2, but this is 0. And now what I can do is that I can take it to the other side. So gamma 1 contour integral dz equals to minus gamma 2 contour integral f of z of dz. But now if I reverse the direction of this integral in this direction, then I can flip the sign. So let's call this, say, gamma 2 prime. So this is gamma 2 prime. So that means that if you have a contour integral over an open loop, an open contour of some holomorphic function, and if you deform that contour to another contour such that you don't cross any singularities of that function, then the value of the contour integral remains unchanged. It's a path independent. It's a path independent integral as long as you don't come across any singularity of the function. You have seen this sort of things in electrostatics, right? And electrodynamics.
Actually, I didn't do electrodynamics yet.
Okay, when you do, you will see similar things. Okay.
Is it like the action of paths, something like that?
No, I mean, it's just like, this is just a, I'm just answering your question why, this integral doesn't have to have an S1 as long as it's a closed loop and the loop does not include any singularities, any other singularities. Of course, this doesn't, then, this is going to be, this result will be unchanged. Okay, so.
Yes, understood.
You can show this very easily. Just think about it a bit carefully. And in fact, the way that we'll prove Cauchy's residue theorem will help you, be able to understand the proofs. Okay, so now next we are going to prove Cauchy's residue theorem as our last thing today.